This is section 2.5, zeros of polynomial functions. Now, finding zeros of polynomials is one of the most important things that you'll ever do in Algebra 2 or pre-calculus. It's also going to be important in calculus. A bit of a warning though, it can be kind of tedious. And things that are tedious are sometimes not liked by students because they involve several steps and they involve being careful. So just to give you a heads up, this section is not an easy section. You're going to have to pay extra attention and make sure that you copy everything down on the screens. I'll work with you in on the problems in class, but definitely pay attention and stay attentive and diligent during this lesson. A polynomial function is a function of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1, etc., etc. Now, that's really just a complicated way of writing something that you've been doing already ever since Algebra 1. And really what we're doing this for is because we just want to make sure that that you understand all the terms that you need to understand. All right, so the polynomial function has a leading coefficient a sub n and degree n. Let's just, I think the best way to do this is looking at some examples. Find the leading coefficient and degree of each polynomial function. All right, so here's our first example. F of x equals negative 2x to the fifth plus 3x cubed minus 5x plus 1. Now first, before you identify the leading coefficient and degree, let's just see how this specific function fits in with up here in the top of the screen the general function that is written in that complicated math symbolism, which often confuses people more than it helps. But look at this a sub n. That's just the first constant, which is the coefficient of the x term that has the highest power. That's all we have here. So in this case, our a sub n would be negative 2, and our n would be 5. And then a sub n minus 1 is just the coefficient of the next term. Notice in this specific case that there is no x to the fourth term. And so what we would do is we would consider that the same as 0x to the fourth. 0x to the fourth is just 0. And so as a placeholder, we could write this polynomial function as negative 2x to the fifth plus 0x to the fourth plus 3x cubed plus 0x squared minus 5x plus 1. It's really just the same thing. All right, pause the video, fill in the blanks for the leading coefficient degree for this, and then resume when you have that answer. Okay, you should have written negative 2 and 5. The leading coefficient is negative 2, and the degree is 5. So a sub n is negative 2, and n is 5. How about for this example, f of x equals x cubed plus 6x squared minus x plus 7. Pause the video, write the leading coefficient and degree, and then resume when you have those. So you should have come up with 1 and 3. The leading coefficient is 1 because 1 is the coefficient of the x cubed term, and the degree, or the number of the highest exponent, is 3. All right, here's kind of a hard one. F of x equals 14. That's just a constant, right? It would look like a horizontal line. That's all that graph would look like. But it does have a leading coefficient and a degree. Pause the video, try to figure that out, and then resume if you get stuck or when you have an answer. 14 and 0. Okay, the leading coefficient is 14 because 14 is the only coefficient, so it must be the leading coefficient. And also the degree is 0 because 14 is the same as saying, 14 times x to the 0. Since x to the 0 is 1, well, 14 times 1 is 14, therefore the degree of this simple constant function is 0. A number a is a 0 of a function y equals f of x only if f at a equals 0. All right, now that is a complete review for you because by this time you should know what a 0 is, but we're going through this screen just to make completely sure, we're just making ourselves completely sure that we understand what these terms mean. All right, so remember that when you're trying to find zeros, you set the function equal to 0. That's why we have here on the upper left corner of, I'm sorry, the upper right corner of the screen, f at a equals 0. All right, so what that means is that x equals a is a 0 of f. In other words, if you plug a in for x in the function, you end up with a value of 0, so that's a 0 of f. You could also say that x equals a is a solution of the polynomial equation f of x equals 0. This is just spelling out what you already know. But x equals a is a solution of the polynomial equation f of x equals 0. X minus a is a factor of the polynomial f of x. So if a is a 0, then x minus a must be a factor of the polynomial. And you know that from Algebra 1, right? Like if you factor a quadratic equation and you get something like x minus 2 times x minus 1, well, when you're finding the zeros, you know that the zeros are 2 and 1, because when you plug in 2 or you plug in 1, you end up with 0. So x minus a is a factor of the polynomial. And finally, a0 is an x-intercept of the graph of y equals f of x. Remember that 0 and x-intercept, those are synonyms. And another synonym that's not on this table is a root. We can sometimes call a0 a root of a function. And we can call an x-intercept the same as a root of a function. A polynomial function of degree n has exactly n zeros, real and complex. Now, in yesterday's section, we talked about complex numbers. That was a preparation for today's lesson, because complex numbers can be zeros, and we saw that in the last example of the last lesson. Complex numbers can be zeros. Now, when you're asked to find only the real zeros, obviously you wouldn't include the complex zeros. But in this lesson, we're going to be talking about the complex zeros and the real zeros. So if a polynomial function of degree n has exactly n zeros, that means it has exactly 5 zeros if it's of degree 5, or it has exactly 3 zeros if it's of degree 3. Now, those 5 zeros, for example, if we're talking about a degree 5 polynomial, those 5 zeros could be any combination of real and complex. It might be 3 real and 2 complex. It might be 1 real and 4 complex. But the total number is going to be n. Now this principle of the degree number matching the number of zeros, that principle comes from the fundamental theorem of algebra. And Friedrich Gauss, you remember Gauss from Gauss's formula back when we were doing Gaussian elimination. Well, Friedrich Gauss came up with the fundamental theorem of algebra, and the consequence that he derived was that a polynomial function of degree n has exactly n zeros. Now, the complex zeros always occur in conjugate pairs. So that means that you're always going to have an even number of complex zeros. You might have 2, you might have 4, you might have 6, but you're never going to have one by itself. And that helps because if you find one complex zero, you automatically know what the other one is. If you find a plus bi, the other one's going to be a minus bi. Now in the next few screens we're going to see specific examples of these principles. But for now it's important that you write them down because you're going to be referring to them later. Example, find all the zeros of f of x equals x to the 4th minus x cubed minus 2x squared. The first thing we do is we factor. And when we factor this, we take the x squared out, and we factor it to be x squared times x plus 1 times x minus 2. Now with your experience in Algebra 2, you can probably identify already what the zeros are. Because you know the zeros are any numbers that you plug in for x that would yield a result of 0. And so it's clear here that if I plug 0 in for x here, then the whole thing is going to be 0. If I plug -1 in for x here, the whole thing will be 0. And if I plug in 2 for x here, the whole thing will be 0. Therefore the zeros are x equals -1, x equals 0, and x equals 2. These correspond to the x-intercepts. It's the same thing. Zeros are x-intercepts. So this is what the graph looks like. And we have our three zeros labeled here. -1, 0, 0, 0, and 2, 0. Now you might be asking, well, this is a degree 4 polynomial, and yet it has only 3 zeros. Well, there's an answer for that, because actually it has 4 zeros. And that's because since x squared is the same as x times x, x equals 0 is considered a repeated 0. And so it gets counted twice. It gets counted twice. Alright, so if you wanted to be really thorough about this, you would say that the 4 zeros of the function x to the fourth minus x cubed minus 2x squared are -1, 0, 0, and 2. So this function has a total of 4 zeros. And of course that matches the degree of 4. The rational zero test. Okay, here's where it gets tedious. Alright, here's where it gets tedious, so be patient. Write down everything that's on the screens and pay attention to the examples as we apply the rational zero test. If a polynomial f of x has integer coefficients, every rational zero of f has the form p over q, where p and q have no common factors other than 1. Now, what are p and q? P is a factor of the constant term, and q is a factor of the leading coefficient. Now, this probably doesn't make sense yet, and hopefully you're writing it down because we'll need to refer to it. But everything will become clear when you see the specific examples. Example, find all real and complex zeros of f of x equals x to the fourth minus x cubed plus x squared minus 3x minus 6. Now, you can probably recognize just by looking at this polynomial that finding the zeros is not so easy as the last example, because you can't just factor this thing. And that's why we have the rational zero test, because what the rational zero test allows us to do is to test certain possible zeros to see which numbers are actually zeros. Alright, now before we get into that, let's make sure we mind our P's and Q's, so to speak. I don't even know if they use that expression anymore. I remember when I was a little kid, my mom used to say that, mind your P's and Q's, which meant, be careful with your manners. But here, when we're talking about minding our P's and Q's, we need to make sure that we know what the P is and what the Q is. Alright, and so the P is just the constant. And if there is no constant there, then it would just be 0. And actually you wouldn't really be able to use the rational zero test, because if p is 0, then 0 over anything is 0. And the only thing you could test is 0. But when we apply the rational zero test, we have normally a non-zero constant at the end, and that becomes our p. And our leading coefficient is our q. Our leading coefficient is our q. Now, when we're trying to factor these, we have to ask ourselves, all right, what are the possible rational zeros? Well, we know that rational zeros are going to be of the form p over q. And that's where p is a factor of the constant term, q is a factor of the leading coefficient. So what are the different factors of -6? Well, 1, 2, 3, and 6, because we have 1 times 6, either +1 times -6 or -1 times +6. Those are factors of -6. We also have 2 and 3, either +2 times -3 or -2 times +3. Those are factors also of -6. And factors of 1, well, that's easy, right? It's just 1. And so that makes it simple to find the possible rational zeros. They're all the different p over q combinations. So plus or minus 1 would be the same as 1 over 1. Plus or minus 2 would be the same as +1 plus 2 over 1 or minus 2 over 1. Plus or minus 3 would be the same as 3 over 1, negative 3 over 1, etc. Because all my different p's are 1, 2, 3, and 6, plus and minus of all those, and my different q's is just 1, and so that makes it simple. The possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now the rational zero test only tells us what the possible rational zeros are. It does not actually tell us what the zeros are, and that's where synthetic division comes in. Because what you're gonna do, and this is why it gets a little bit tedious, is you actually have to use trial and error and try different rational zeros. Now the good news is you're not going to have to try every single possibility, because normally you can find some of the possible ones early, and that will eliminate a lot of work. But the fact of the matter is that it is a bit of trial and error, and without a calculator, this is really how you need to do it. Now, of course, you can find real zeros easily on your calculator, and some calculators even give you real and complex zeros. But as I've said before in the class, there are several good reasons to learn how to do things without a calculator. For one thing, you might lose your calculator, or maybe it just freaks out on you and doesn't work anymore. Maybe the batteries go dead. Maybe you come to a certain part of the test, either the ACT or the SAT, or a certain part of the test where they don't let you use a calculator. And even beyond all those practical reasons, there's the simple fact that learning how to do math without the calculator is actually learning math. Just depending on your calculator all the time is simply learning how to use a tool, but not understanding the math behind it. Okay, so let's proceed. We know that plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6 are all possible rational zeros according to the rational zero test. Now we need to test each of those possible ones to see which ones work, and that's where we're going to use synthetic division. Alright, so we use synthetic division to test the first few possibilities. Now we've gone through synthetic division before, so I don't need to explain it, but let's just make sure we understand where this comes from. 1, follow the arrow, 1, actually I'll use a pen. See, this 1 matches up with that 1. This negative 1 matches up with that negative 1. This negative 3 matches up with that negative 3. Oh, and this 1 in the middle matches up with that 1. And this negative 6 matches up with that negative 6. Okay, let's follow the lines, okay? See how this 1 is just the coefficient of x to the 4th. This negative 1 is simply the coefficient of x cubed. This 1 is simply the coefficient of x squared. This negative 3 is the coefficient of negative 3x. And this negative 6 is the constant term, negative 6. Alright, so then we're going to use synthetic division, and we're going to test one of our possible rational zeros, which is 1, the number 1. We're just going to start with that and see what happens. Well, when we apply synthetic division and we test to see if 1 goes evenly into the polynomial, well, we find out that it doesn't, because this negative 8 over here is a non-zero remainder, and therefore we know that x minus 1 cannot be a factor. It can't be a factor. And 1, therefore, cannot be a 0. Alright, so we throw out 1. Now we have to test negative 1. And so doing synthetic division on negative 1, we get this. We divide negative 1 into it, and we end up with a nice 0 remainder. And what that means then is negative 1 is a 0. Negative 1 is a 0, and the whittled down function is x cubed minus 2x squared plus 3x minus 6. Alright, let me explain what I mean by whittled down. Alright, you know how, like sailors in those old sailor movies or books, when they're out at sea and they have a long trip, they need something to do. Well, they often whittle. Well, they take a block of wood and whittle away until they get a nice little shape, some kind of nice statue or figurine out of that little block of wood. So you know what whittling is. Well, whittling then is shaving away bits of wood until you end up with something smaller and more formed. Well, that's what we're doing here in math. Because we have found out that -1 goes evenly into this polynomial, and that -1 is a 0, then we have whittled down the function to x cubed minus 2x squared plus 3x minus 6. Okay, so where do we get those numbers? Well, this 1 in front of the x cubed matches up with that. This -2 in front of the x squared matches up with that. This 3 in front of the x matches up with that. And this -6 matches up with that. Now, we recall when we were doing synthetic division, and this is why it's important to take good notes, because sometimes you need to refer back. You should be able to refer back to your nice, neat notes on our synthetic division section. And there was a part there where we proceeded with the synthetic division using the whittled down function and not the original, because it saves steps. And there was even an explanation in that video of comparing it to arithmetic, showing that if a factor goes evenly into the whole thing, it'll also go evenly into a part. All right, so the whittled down function is x cubed minus 2x squared plus 3x minus 6. And what we can do now is, instead of applying synthetic division to the big polynomial, where we have 1, -1, 1, -3, -6, we can now apply it to this smaller whittled down polynomial, and that will save us steps. Alright, this is exactly what was written on the last screen. Just to carry it forward, -1 is a 0, the whittled down function is x cubed minus 2x squared plus 3x minus 6. So now we're going to use that function for our next steps of synthetic division. Alright, let's test the next one on the list, 2. Does 2 work? Well, it turns out that it does. Notice that this 1, -2, 3, -6 corresponds to, up here, the 1, the -2, the 3, and the -6. We're testing to see if 2 is a 0. Using synthetic division, it goes in evenly because we get a 0 remainder. Therefore, 2 is a 0, and the whittled down function is x squared minus 0x plus 3. Just to be extra clear about where we get that, this 1 in front of the x squared corresponds to this 1. This 0 in front of the x corresponds to this 0, and this 3 corresponds to this 3. Alright, so we have our whittled down function of x squared minus 0x plus 3, which is the same as x squared plus 3. The factored function is x plus 1 times x minus 2 times x squared plus 3. So see what we did here. We used synthetic division to factor something that was otherwise not factorable. We know that x plus 1 is a factor because we already found that -1 is a 0. And since if you plug -1 in here for x, you get 0, then x plus 1 must be a factor. We know that x minus 2 is a factor because we found that 2 is a 0 of this polynomial. Plugging 2 in for x, you get 0. And then we end up with x squared plus 3 because that's our final whittled down function. And at this point, we don't need to proceed further because this is a fully factored function. From this, we get the real zeros and the complex zeros. The real zeros of f of x are -1 and 2, and the complex zeros are plus or minus root 3i. If you plug in root 3i for x, and you square it, you end up with -3. -3 plus 3 is 0. And if you plug in negative root 3i for x, and you square it, you end up with -3. And -3 plus 3 is 0. So we've now found the 4 zeros for this polynomial function. And those 4 zeros are -1, 2, positive root 3i, and negative root 3i. There are 4 zeros in all, which matches the degree of this polynomial. And since this degree was 4, there are 4 zeros. Next example, find all real and complex zeros of f of x equals x to the fifth plus x cubed plus 2x squared minus 12x plus 8. Okay, here our q is 1 and our p is 8. Well, I'd like you to do this example in two parts. So first, pause the video, apply the rational zero test and synthetic division until you find two different zeros. And then at that point, once you've found two zeros, I'd like you to resume the video because I want to show you something that could save you time. Otherwise, you might spend too long on this example. So again, we're going to do this in two parts. For now, pause, do the rational zero test and synthetic division until you find two of the zeros, and then resume, and I'll walk you through the rest of it. Okay, so the first part, we apply the possible rational zero test and find that the possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. We use synthetic division to test the first few possibilities. The first possibility is 1. Let's just start with 1. And when we do synthetic division, we find this. Now notice the top row here in the synthetic division. This 1 corresponds to 1x to the fifth. This 0 corresponds to 0x to the fourth. It's just a placeholder. This 1 corresponds to 1x cubed in our original polynomial. This 2 corresponds to 2x squared in our polynomial. This negative 12 corresponds to negative 12x in our polynomial. And this 8 corresponds to the constant in our polynomial. Okay, so doing synthetic division with 1 as our possible rational zero, we find that we end up with a zero remainder, which means that 1 is a zero of this polynomial. So 1 is a zero, and the whittled down function is x to the fourth plus x cubed plus 2x squared plus 4x minus 8. Again, just to be crystal clear about this, because it doesn't hurt to repeat, this 1 in front of the x to the fourth corresponds to this 1. This 1 in front of the x cubed corresponds to this 1. This 2 in front of the 2x squared corresponds to this 2. This 4 in front of the x corresponds to the 4. And this negative 8 constant corresponds to this negative 8. Alright, so we have 1 as our 0, and we have the whittled down function. We are now going to use the whittled down function instead of the original function because it's going to save us time, fewer numbers. So now we're going to perform the synthetic division on the next thing that we'll test, which is negative 1. We already tested positive 1, found that it's a 0. Now let's test negative 1 because we know that it's in our list of possible rational zeros. And when we do synthetic division using the whittled down function, 1x to the fourth plus 1x cubed plus 2x squared plus 4x minus 8, we find that negative 1 does not go in evenly because we end up with a remainder of negative 10. So now we're going to try 2. Let's see if 2 works. Well, we do synthetic division with 2 on the same whittled down function, and we end up with a remainder of 32, so 2 is definitely not a 0. So now let's try negative 2. And sure enough, negative 2 does work because when we do synthetic division with negative 2, we end up with a remainder of 0. And so negative 2 is a 0, and the whittled down function is x cubed minus x squared plus 4x minus 4. And that comes from this 1 in front of the x cubed corresponds to that 1. This negative 1 in front of the x squared corresponds to that negative 1. This 4 in front of the x corresponds to that 4. And this negative 4 corresponds to that negative 4. Okay, bringing that forward again onto this screen, negative 2 is a 0. The whittled down function is x cubed minus x squared plus 4x minus 4. Okay, now this is the part where I asked you to resume again because you know, at this point, you could keep doing the synthetic division, but it's going to end up wasting a lot of time because I want to show you a trick that you can often use. Once you've found 1 or 2 of the rational zeros, then you can try to factor. And so the partially factored function is x minus 1 times x plus 2 times the final whittled down function that we ended up with. Okay, now we know x minus 1 is a factor because 1's a 0. We know that x plus 2 is a factor because negative 2 is a 0. And so then what we're left with, besides x minus 1 and x plus 2, is that final whittled down function. And that is x cubed minus x squared plus 4x minus 4. Now, what I said before of how you could end up wasting a lot of time by trying all those other rational zeros is because none of those other rational zeros works. Now, of course, you can't know that ahead of time, but the point is that once you find one or two rational zeros and you've whittled down the function a bit, it's often possible to factor the rest, and that saves you a lot of work. And we actually can factor this now. And by the way, there are times when you end up with the whittled down function and you can factor it, but then if it's only a quadratic function, you can end up using the quadratic formula. All right, so how to factor this? Well, we keep our x minus 1, x plus 2, and then I put in blue brackets what's left, what we're trying to factor. And if I put in brackets what's left, what we're trying to factor, well, I see it here in the red. I'm grouping terms. I believe there was a problem in the earlier section where we had to do that, right? Grouping terms, and so I have x cubed minus x squared grouped together, and I have 4x minus 4 grouped together. And notice there's a pattern. It's the pattern of 1 is to negative 1. Okay, what I mean by that is, look here where the arrow is. That 1 in front of the x cubed is to this negative 1 in front of the x squared, as this 4 in front of the x is to this negative 4. Same ratio, right? And so we can factor out a certain amount. We can factor out the x squared, and we can factor out also the 4. And we end up with x squared times x minus 1 plus 4 times x minus 1. And then since that's basically just distributing the x minus 1, we can write that as x squared plus 4 times x minus 1. And the fully factored function then is x minus 1 times x plus 2 times x minus 1 times x squared plus 4. Now from that we can get our zeros. The real zeros of f of x are 1 and negative 2. We found that already with synthetic division. And notice here that after fully factoring this polynomial, we see that 1 is a repeated 0. 1 is a repeated 0. See, we have x minus 1 here, and we have x minus 1 here. And since it's a repeated 0, it gets counted twice. And the complex zeros are plus or minus 2i. If I put 2i in for x and square it, I get negative 4. Negative 4 plus 4 is 0. And if I put negative 2i in for x and then square it, I get negative 4. And negative 4 plus 4 is 0. So I found that there are 5 zeros in all. I have 1, 1, negative 2, positive 2i, and negative 2i. So I have 5 zeros in all, and that matches the degree 5 of this polynomial. The classwork, page 180. Please write these numbers down. And you have to do 103 A, B, C, not D. And we'll work on these in class.